Physicist by training, but I've been working with disease modeling and surveillance for quite a while now. I'm a researcher, public health researcher at Fiocruz, the scientific computing program, working mainly with surveillance of respiratory infections in Brazil. I have worked also with disease propagation models and also the incorporation of mobility data into propagation models and so on. And the focus of my classes here on this school will be to go over a little bit the details behind the actual data that we have on the field. So try to assess a little bit how do we go from the models that are being discussed on the other classes to what we actually have in terms of data on surveillance and from disease notifications in different countries, and how those things can sometimes make quite difficult to incorporate those data into analysis, especially if we want to run models in real time, right? Because it's one thing to analyze a disease retrospectively. Another one is to provide updates and analysis on real time. So while the disease is going on, to provide estimates of how many cases we have, what is the future prospects, and analyze scenarios. And then and this to understand what are the particularities of the available data is extremely important for us to actually provide analyses that are in fact meaningful. And it's really important, as I hope it will become clear along those the next few days, that there are several pitfalls and particularities that we must try to understand before actually implementing any data feeding into our models. Okay, so first of all, let me start by, so today, there will be, the class today will be more in terms of discussion on some of the, some particularities of data, and the next one we will go a little bit into some analysis per se. So today I want to start, first of all, so in the last two sessions, we discussed, both teachers went over case counts, right, and models that have the need to incorporate the number of cases, right, that are going on for whatever disease you are analyzing. Now, I want to ask you, well, what exactly do we mean by a case? So take for instance, dengue case, let's say. How do we define an actual case of dengue? Does anyone have any proposal of how can we define an actual case of dengue? Clinical test is the way to go if you want to have confirmed cases, right? But so if you do have confirmed cases, you are guaranteeing that all the counts that you have are in fact related to that particular disease, right? But there is one pitfall that also Roberto mentioned a little bit, is that, okay, but how do I actually implement that? Is it feasible to actually test everybody? Usually no, right? And there is another issue that, well, you can restrain yourself to testing individuals that goes to a clinic, right, that seek medical care. This is one way to go, right? And you could also restrict yourself to hospitalized cases of a given infection, right? So in the first case, so we can have what we call ambulatory care or so cases that do not need hospitalization, right? So you're thinking about mild to moderate cases. You can have a focus on hospitalized cases. Now, and still, if we only think about confirmed cases, those two will not be the same thing, right? Because hospitalized cases will be usually just a percentage of all the cases, even of the confirmed cases that we have, right? So we can think that you have hospitalized cases, and then you have all the light to moderate cases. Some of those might evolve in terms of severity, that those individuals become hospitalized at some point, right? But then you also have individuals that even if they seek medical attention, be it light to moderate cases, be it more severe cases that need hospitalizations, there are some pitfalls in the testing itself. What are some of the possible pitfalls in focusing on testing, even if we actually manage to test everybody that seeks medical attention? Sorry? False positives is one thing. False negatives is another thing, right? And those two things, they will depend on both the quality of the test being implemented, right? Type of testing. It's also another important issue. So if we go back to the COVID-19 example, for instance, at some point in the beginning of the pandemic, a lot of places invested in using IgG and IgM tests, right? So serotyping. Once we moved on into the understanding of the particularities of that particular disease or that particular infection, it became clear that those type of tests were not able to identify active cases, right? They were able to identify previous cases, so cases that had occurred at some point in time, but were not necessarily still infectious, okay? And also, after time goes by, we can also lose the positivity related to that particular testing, right? And so we needed, for COVID-19, specifically PCR tests to actually identify active cases, which is what we want in terms of model fitting, right? Because when we think about the I class in the compartmental models, we are specifically thinking about individuals that can transmit the disease, right? So previous cases, I don't want. So for that particular test is not interesting for us, right? But even if we use the adequate test for the particular infection that we want to focus, there is also the issue of sensitivity and specificity. Which are related to false positives and false negatives. So we will always be losing some cases, right? Unless we have a test that is 100% accurate. which is usually not the case for any particular test or disease. Okay, so we'll be always missing some cases, right? So this is one pitfall. Of course, the better the testing, the better those two characteristics, and more accurate it will be to identify active cases. But still, there is the issue of when is an infected individual seeking medical care. So the time between symptom onset and medical attention. So the time of testing itself. This is also an important issue in being able to positively identifying an active case. So you have pitfalls that are related to the quality of the test itself. You have issues that are related to individual choices and also severity, right? Because if a given disease is usually leads to light to mild cases, the likelihood that an infected individual will actually seek medical attention, you expect to be lower. And if they don't seek medical attention, they will not be tested. Right? So we still have another layer that are individuals that did not seek, that in all the positive cases, only those are the ones that we are assuming that will actually seek medical care, and still within those, only part of them will be correctly identified due to time to seek medical attention and quality of testing. And if this was not already enough, we still might have an issue of asymptomatic cases, right? That we might think as part of those individuals that will not seek medical attention, right? So, quality, timeliness, and also issues related to severity or health unit access. All of those compete against measuring the correct number of active cases that are currently happening. Now, in terms specifically of quality and also somewhat related to timeliness, what could we do about in terms of those individuals that are seeking medical attention, but for some reason either they are not tested, or the time window is out of pace, or the test is not good enough? How could we propose an alternative method of identifying possible cases that are might not be affected by those two issues? Anyone think of a possible alternative way of defining a case that is not necessarily related to testing itself? Sorry? Environmental surveillance could be, okay. This could be, but then you have the issue of how this is something that is used. There is an important issue of how do you go from environmental surveillance to how many cases? Okay, this is a very, very important problem and a very serious problem. Usually, not always, but usually what people do in terms of environmental surveillance is to identify either a specific pathogen is present or not. Presence and trend, but not necessarily volume of cases. Okay, so we can have an idea of whether a given pathogen is circulating in a given region, and either it is the number of cases is going up or down from how many specimens you are identifying in your control sampling process, but the actual number of counts, this is something else. Okay. Yeah. Yeah, exactly. But again, from going to number of cases is another issue. And for the models that we are that we have been discussing in the today on the previous lectures, what we need is actual number of cases, right? So another approach, possible approach, is still relying on medical attention, is to take into account the symptoms of a given disease. Okay? So for instance, for respiratory infections, be it influenza, be it COVID, or be it or adenovirus, rhinovirus, and syncytial virus, for instance, usually what we do is that we proposed a case definition that usually take into account whether an individual had fever or not, if it has is presenting signs of coughing or sore throat, if it has any signs or symptom of difficulty breathing, right? Those are symptoms that are common to flu cases, right? But not only flu cases, right? So this is a possible approach, what we call a syndromic surveillance. Where you are relying on the symptoms itself to identify now probable cases, right? Because when I'm relying only on the symptoms shown or symptoms present, I cannot guarantee that all of those cases are in fact related to the particular disease that I'm interested, right? Why? Because we have several infections, several pathogens that might lead to the same symptoms. Again, respiratory infections is a classical example. Be it influenza, be it COVID, the usual symptoms are very similar for all of those. So how can I separate and guarantee that a given individual that is presenting a set of symptoms that are related to influenza-like illness is in fact influenza or another respiratory infection? I have to go back to testing. So there is a trade-off here. With a syndromic surveillance, I'm amplifying my net, but I'm also accepting the possibility that I'm including garbage in what I want to see. If I rely specifically on confirmed cases, I am certain that what I have is actually what I want, but I am losing cases that for some reason the test became a false negative, right? So there's a trade-off here.
What is the advantage of using symptoms
There's a very, very good question. Now, in a syndromic surveillance, what I can do then is test a subsample of those syndromic cases, right? So with that, I will, of course, I will still have an issue with these, but then I can use the proportion of positive cases on the subsample that I am testing and extrapolate to the total cases that I am observing in my syndromic surveillance. This will make it cheaper because I won't have to test everybody, right? And if my sample is done properly, it will be able to identify what is the viral population, that is, what are the pathogens that are related to what I'm seeing, and what are the ones that are dominating, the percentage associated to each, okay? So I will still have some issues there, but at least I will make it cheaper to run, and I can then assume that a certain percentage is being lost due to the quality of the testing itself. Okay? Is it clear so far? Now, so those are some of the issues related to case identification. But and finally, there is another important point that is also related to what we're discussing here, is that, again, going back to the models, what we want is individuals that are able to transmit. So asymptomatic cases, depending on the disease, is not an actual problem. Because it might, some diseases, a lot of them, asymptomatic individuals are not able to transmit, or the probability of transmission, the transmissibility rate is extremely lower than symptomatic cases. So I can ignore the asymptomatic. This is not always the case, but for some diseases, it is. So again, depending on what I want, on what is the disease I'm studying, I have to understand all of those aspects to define my surveillance structure, and then to take into account those particularities to define my surveillance, then with the observations that I have, then use those observations into the compartmental model that I'm using to model the propagation process. Now, one final thing here still. Put it up. See here. If my surveillance is based only on hospitalized cases, and my model is an SI type of model, supposing that the process of counting cases is already perfect in terms of hospitalized cases. So everybody that is hospitalized, I am being able to identify it correctly. So I have the correct number of new hospitalizations. Is this information already sufficient to plug in this model? Yes or no? What are the compartments that we have here? Susceptible and infectious cases, right? Yeah, but if I know what is the size of my population, I can go from one to the other, right? But that's not all. My point is this information sufficient? It's already what I want here? No. Why not? right? You're not taking into account the mild cases, the light and mild cases. I'm only looking at severe cases. And usually this is just a fraction of what actually is circulating. Not only that, those individuals here, do they have the same, usually in general, the same ability to transmit to others in comparison to those that are not hospitalized? No, because they are already institutionalized. They are not circulating in the population. So you assume, you would be right to assume that when Roberto was mentioning the average number of contacts per unit of time, hospitalized individuals and non-hospitalized individuals, it is to be expected that the average number of contacts will be completely different, right? So not only those are not all of the individuals, but also they are likely to have a lower beta associated to them, right? Because they are interacting with less individuals than those who are not hospitalized. How can we go from that, from hospitalized to actually active cases? So one possibility, so we have several important aspects here. First of all is the probability of an infected individual becoming hospitalized at any given point in time. So this is related to the severity of the disease, right? The more severe a given pathogen it is, the higher the probability of being hospitalized. So the closer the number of new hospitalized individuals will be to the number of new cases that I have. The lower the severity, the lower will be the percentage of individuals that are hospitalized, so the farther away I will be from the actual number of infected cases, right? Okay? So far, so good? So this is already one parameter that we need, right? Another one is, well, how long does it take for an infection to evolve to the point of needing hospitalization, right? So then we are looking at the time scale of the natural history of the disease, the time between infection or symptoms onset to hospitalization for those that do become hospitalized at any given point. That I will call here tau H, the time, average time to evolve into a hospitalization, which I could, if you recall the what Roberto did in terms of identifying what was the link between the parameter gamma that was related to the removal of infectious individuals from the compartment of the infected ones. This time here, I can also associate with a rate related to individuals that are infected becoming hospitalized, right? Because I have what is the characteristic time of that process. So I can do something similar to this and have a parameter, a rate that is associated to the inverse of this characteristic time, okay? And what does this mean? This means that usually what we expect if I have here, suppose that this is the curve associated to hospitalized cases or new hospitalizations. If I have a characteristic time, tau h, associated to the development of severity needed to leading to hospitalization, what do I expect if I compare this curve with the let me put here new cases I of t. Just a shift in time, right? I'll have a difference in scale that is associated with the severity, right? The probability of becoming hospitalized. And also, I will have a displacement in time that is associated to the characteristic time between case evolution to severity to hospitalization. Okay. So those are two things that we have to take into account if the disease that I'm studying in a given territory, if I know that the surveillance system associated to that particular disease is tracking only hospitalized cases, I must take into account at least those properties to have what I need to plug into my model, right? Otherwise, what I'll be plugging in terms of new cases will be completely off, not only in terms of volume, but also in terms of time, right? Okay, sure. Sorry? You must. So this is what I was mentioning about understanding and knowing what is the process of case count, of the underlying process of case count before plugging any data into a compartmental model, right? Because if you don't know what are the actual particularities of those cases that are being observed, I can be completely off, okay? So you must track those down. And this in terms of, and we see in practice, in practical applications, it's not unusual, unfortunately, to have those things being mixed and leading to actually wrongful assumptions in terms of modeling, okay? What I can do, though, is if I'm not interested in actually plugging into a mechanistic model, what I can do by only having the hospitalized cases is an estimation of what is the current scenario, right? To analyze whether the number of cases are increasing or not, this is already sufficient. If the probability is at least large enough, right? Otherwise, if the majority, the vast majority of cases are only light and mild, looking into hospitalized cases can throw me completely off the track, right? So again, depend on the particular disease, and also the time scale is also important. But if the time scale is sufficiently close and the percentage of hospitalized cases is not extremely low, I can use a surveillance system based on hospitalized cases to actually make assumptions or actually to identify what is the current situation, the current scenario on a given place. Okay? The issue is in terms of modeling the propagation process itself. Okay? Those are two different things. One is to analyze the current situation, another one is to make projections with mathematical models. This is what I'm trying to assess here. So this is one of the important points that we have to take in mind. For instance, examples here. Again, for dengue, Zika e chikungunya, at least in Brazil, the surveillance is based on ambulatory cases, and at least in principle, every individual that seeks medical attention and shows compatible symptoms should be notified as a possible dengue case or chikungunya case. Zika is not, it doesn't have so much attention right now, but at least for dengue and chikungunya, they should be. So it's not only ambulatory, but it's also, at least in principle, universal. What do I mean by universal? That all cases that are observed in healthcare facilities should be, at least in principle, notified. So I can assume that in principle, all cases are being tracked. Okay? Of course, we have still the issue of testing, but at least in terms of probable cases or suspect cases, this is what we have in Brazil, okay, for those particular diseases. Now, for influenza-like, so respiratory infections, we have two main branches, not only in Brazil, but in several countries. An ambulatory surveillance that is based on sentinel units, what do we mean by sentinel units? That only specific healthcare facilities are expected to report new cases. Okay, so the healthcare authority in the territory defines what are the hospitals or the outpatient facilities or clinicians or whatever that are associated with the surveillance effort for that particular disease, and only those will be notifying new cases. What is the impact on that? That I'm only seeing, again, a fraction of what is going on, okay? So this is the opposite of having a universal surveillance. We will go into some of the details in a few moments. And then we have hospitalized cases that in Brazil and and also in a few countries, it's at least in theory universal. Okay, in Brazil we have some issues in terms of regulation, because it leaves room to only notify those that have a positive test for new strains of influenza or to SARS-CoV-2 and so on, but it at least in principle designed expecting to be universal in terms of hospitalized cases. Now, in terms of sentinel units, now, if I want my surveillance system based on sentinel units to be able to provide analysis in terms of historical trend, current situation, and being able to be used to inform predictive models or mechanistic models, what are some of the characteristics that I need for that particular design to actually be able to provide that kind of information? So let's go in. Let's divide this in parts. In terms of objectives. So in terms, if one of my objectives of my surveillance system is to be able to provide analysis of what is the current activity to inform me whether the current situation is below what is expected, it's compatible to what I expect, or is already exacerbating my population, that is, it's already higher or significantly higher than what I expect. What are some of the characteristics that I must have in terms of those sentinel units? If, let's see, if I want to compare, to understand, to identify what is the current activity level, I need to have a baseline, right? I need to know what is expected, right? So I need historical data, stable historical data, right? To be able to estimate by any given method. We will go in the next few days on some of the methods to try to do this kind of calculation. But I need historical data that is comparable along the time. What do I mean by that? If the sentinel units that I have on a given year are completely different than the sentinel units that I have on the next year, will the number of cases be comparable, yes or no? If I change my sentinel units, is it possible to, in principle, compare what I have now with what I had before? Let's say that my sentinel units in 1 year are on on the outskirts of my city, of my municipality. Okay, so I run for 5 years on the same, my surveillance system on a healthcare unit that is on the outskirts of my municipality. And then, after that, at some point, I change my sentinel unit from that specific site to the central area of the same municipality. What I am tracking, do I have any guarantee that are compatible in terms of volume? No. Right? This is central. If I want to be able to estimate what is, or to assess what is the current activity level based on historical data, and I must have historical data in order to do that kind of analysis, the set of sentinel units must be stable over time, right? So I need homogeneity in time. If the sentinel units are changing all of the time, it's very likely that I will lose this ability.
Marcelo, I want to get this baseline. You need a stable situation about over what time frame? 5 years, 10 years, 2 years?
So it depends on a few things. The first of which is whether the disease that I'm tracking is seasonal or not. What I mean by being seasonal or not. If I look over time and I have a pattern, that is at least more or less repetitive, this is what we call a seasonal effect, right? I can define when I usually have high or low activity. This pattern repeats itself, so it's kind of a stable oscillatory system, right? Now, if I have this property, then I need to have at least, depending on the method, at least 3 to 5 sequences or seasons. And then the question is, well, how long those seasons take? How long are the seasons for that particular disease, right? Usually, several diseases that do show seasonal pattern, the pattern is usually year-long, right? So every year it repeats itself. So in principle, you need 3 to 5 years of data to be able to do this type of analysis, okay? Now, if I have a disease that is more or less stable and from time to time have outbreaks, then having this chunk is already enough for me to identify what is the expected number of cases and identify when I cross this threshold, okay?
Because I was thinking about dengue, which is kind of seasonal, but it's not like this one. It's very big some years, and then the next season is a small season, which could create a lot of variability, which means probably you need more years in order to have not only the mean, but also some variance.
Yeah. So for dengue, for instance, what we have is, well, now it's a little bit messed up, but we used to have something like a 2-year pattern of high activity. We always, well, not always, but usually you see a clear peak during the summer, but the intensity or the amplitude of the peaks would change on a more or less 2-year basis, okay? So what you would have is something like, let's say, or something like that, okay? Now, depending on the method, there are methods that focus, that try to estimate, to assess activity levels by looking at what is the baseline at each season. In that type of approach, the fact that the peaks are varying is not that much of a problem, unless the lower peak is similar to the baseline of the higher peak year, because then it messes up how can I identify what is baseline and what is high activity. Okay, so you'll see in the next classes that the process of going through this type of analysis, it's still in its more or less, although people have been studying for quite a while now, it still needs a lot of advancement in terms of methodology to be able to deal with those characteristics, especially when the seasonality is not that clear. Okay, but this is something for the next classes. But in general terms, if I have at least 3 to 5 periods of baseline activity, in principle, I could be able to at least define thresholds for when things are starting to go up. Okay, defining other thresholds for high activity, very high activity, then it's the same process, but then looking at high activity seasons. Okay. So, but going back to what I was saying here. So we have that, first of all, so we need, for activity level, we need sentinel units to be homogeneous in time, right? Another usual objective is to compare across regions or across the territory. Right, so for instance, with my surveillance system, I want to be able to identify if a given pathogen is affecting more a given area than another. Right, I want to know if there is a specific city where I'm seeing higher activity than others, or whether inside the same city, different neighborhoods are seeing more or less cases. For that, what do I need? For activity level, we needed the sentinel units to be more or less homogeneous in time. To be able to compare across space, what do I need? More or less the same idea, but in terms of space. I need my sentinel units to be themselves comparable or compatible across space. For instance, if I have in one area of the city a sentinel unit that is a hospital that is, for instance, focused on maternity care or on geriatric care, the population that is being observed in those two units are completely different, right? One will be attending pregnant women, and the other one, the elderly of any gender. Are those two comparable in principle? Not at all. So the characteristic of the sentinel units must be also homogeneous in space, for me to be able to compare activity across different regions. Do they need, though, to have the same capacity in terms of number of patients attended any given day? No. Why not? It's in that direction, okay? So, what as long as we have what is the basin of attraction of my healthcare units, that is the area that is attended by that healthcare facility, I have an estimate of what is the exposed population. If I have what is the exposed population, I can extrapolate and can calculate the incidence of that particular disease in this healthcare facility, in that territory that is attended by the healthcare unit, and extrapolate to the whole population. So it's not necessary, it's not mandatory that the capacity or the size of each sentinel unit be similar, be homogeneous in space. No, as long as I can identify what is the population that is seeking attention in that particular facility. Is that clear? Okay. What I do need is that the characteristic of the people attending each healthcare unit, that must be homogeneous. Either is a open attendance for all individuals, or all of them are only focused on pediatric attention, only on geriatric attention, and so on and so forth. Okay? So the characteristic in terms of people being attended must be the same. The capacity of attending, the number of individuals attended at each day is not necessarily, does not need to be exactly the same. Okay? Because as long as I have what is the size of the population, I can estimate the incidence, and from that I can extrapolate and compare different regions, different healthcare units. Okay? Is that clear? So this is things that we must take into account, if possible, when we are dealing with sentinel units. And again, this is also extremely important if I want to plug the data that comes from a sentinel unit into mechanistic models. Because again, I need all of the individuals that are active cases, right? The sentinel units will be only associated with a specific place or territory, okay? It's not my whole population. But as long as I can calculate incidence associated with that facility, I can extrapolate to the whole population, and that's it, okay? Now, so this is some general aspects to have in mind. Of course, unfortunately, not all of those details are easily accessible. Okay, so there are some difficulties to identify what is the exact surveillance model, whether it's a sentinel or universal, the characteristic of the sentinel units also is not always easily available, but at least in terms of planning, those are things that must be taken into account so that the people that are using the data can assume that those aspects are being respected in my surveillance system. Otherwise, everything is off the table, are off the table. Now, aside from that, so we mentioned, I mentioned that for respiratory infections in Brazil, we have ambulatory surveillance based on sentinel units. We have hospitalized surveillance of hospitalized individuals that we can assume that is more or less universal. But then, and both of them are based on syndromic surveillance. So all suspect cases should be notified and then later on tested and the database updated with the outcome of the test itself. But it's, they're all syndromic in principle. Now, when we are dealing with syndromic surveillance, we discussed already the issue of specificity, right? Because I might be notifying cases that are not related to the particular disease that I'm studying. But there is also another important aspect. So I already know that I'm dealing with suspect cases, not necessarily confirmed cases. But there's also another important aspect related to syndromic surveillance, which is case definition itself. Okay, so how do I define what I'm calling a suspect case in terms of signs and symptoms? Okay, so in terms of severe acute respiratory infections, so the WHO proposes a case definition that is based on presenting fever, cough, and any sign of difficulty in breathing. Okay, this was used in Brazil before the pandemic. Then in 2020 we had several changes along the years to broaden up the case definition. One of the things that was dropped is that fever was no longer mandatory. Okay, so from before 2020, fever was mandatory. And story. From 2020 onwards, at some point of 2020, actually. And there were some other changes as well. But let's focus on this particular aspect at the moment. So we had one case definition before 2020 where fever was a necessary condition that should be present for an individual to be identified as a suspect case of severe acute respiratory infection. After that, fever was no longer mandatory, and this is on par not only with COVID, but also there is an international discussion of whether fever should or not be mandatory symptoms for respiratory infections in general. But the fact is that we have a single database for severe acute respiratory infections in Brazil that before 2020 had one case definition, and before that started to have a new case definition. What is the impact of that? Are the cases necessarily comparable? Am I able to use data after 2020 to compare with what happened before? No. As is? No. As it is, straight out of the database? No. If I only look at the total counts, I should not compare those two. Why? Because this rule is more strict than this one, right? I will have a subset of cases here that are compatible with this definition, but the other way around is not true. So what I can do, though, is with the data before 2020, if my notification system has on its metadata the list of presented symptoms, then I can, by hand, implement the previous case definition. And now that data will be comparable in principle, at least in terms of case definition, right? So I can restrict my new data to a case definition by filtering the database in order for it to be comparable to what I had before. So what do I need? First of all, I need what was the case definition at each along my surveillance history, okay? And I need my database to have enough information for me to be able to sanitize this process and homogenize my data a long time, okay? If this is not possible, if any of those two are off the table, then there is no guarantee that my data is comparable over time. Is that clear? Again, this has a direct impact into the activity of using real data to model epidemic diseases, epidemic process, right? Because I must have a data stream that is the same individuals that I'm tracking. Otherwise, the number of new cases can be completely thrown off the hook just because the case definition changed. And then I have an increase in number of cases, not because the disease is more severe, but because my case definition is broader, okay? So let's see an actual example here. Now, which is another important point in terms of real data. It is one thing to have a protocol defining case definition to be used for a given notification system, okay? So we have for respiratory infections, there is a case definition for dengue, there are case definitions for several diseases that are notifiable. Now, let's compare in terms of having SARI as an example. What we see in the database, if we look, if we get the same database and count the number of cases that do show that the individual was hospitalized or deceased, because this is the minimum that we need in terms of SARI, okay? I forgot to explicitly say SARI is strictly related to hospitalized or diseased individuals, okay, from respiratory infections. So mild cases are not within the definition of SARI, okay? Mild cases of respiratory infections is what we call influenza-like illnesses, okay? So to be a SARI case, the person must have been either hospitalized or the individual died because of the respiratory infection, okay? So, and luckily for us, in terms of the Brazilian database, there is specific fields in the disease, in the notification system that specifies if the notified cases is associated with an individual that was hospitalized, yes or no, and what was the evolution of the case. That is, if the individual had become cured or died because of the disease. Okay, so we can filter out our data based on those two characteristics alone. Now, this guarantees the minimum, okay, that we are looking at severe cases. Right. But then there is the case of the presented symptoms themselves. This is a comparison taking the official data from 2014 all the way to 2 weeks ago, comparing the difference between the number of counts, okay, in each, the number of counts for all of the SARI cases that have been notified, okay, across the years. Looking only at SARI cases with lab result positive for SARS-CoV-2, so COVID-19 SARI cases, positive for influenza, either influenza A or B, doesn't matter, and finally for respiratory syncytial virus. What we're comparing here, the number of cases at each week that we get if we take into account all of the cases that were notified, regardless of what were the symptoms that were reported. So everybody that we look into the database and just making sure that the notified cases was hospitalized and or died, we take into account. And if we restrict ourselves, we filter the data out, making sure that they respect the case definition. That is, the symptoms are compatible with what we want. And what we see is that for SARI in general, we have about a 20% increase in the total number of cases if we don't take into account the reported symptoms. For COVID, it's for COVID-related SARI cases, it's even worse. It's more than 60%. For influenza, it's about 25, more or less, and for respiratory syncytial virus, is lower than that. But there's a clear difference. How can I guarantee that all the cases that I'm looking at my database are in fact related to the disease that I'm trying to analyze by taking into account the case definition? Okay, because otherwise, there is absolutely no guarantee unless the database is structured in a way that cases can only be uploaded if they respect the case definition, which is usually not the case. Usually, administrators leave the system open so that you do not put too much barriers into data uploading, but then you have the issue that there is no guarantee that there is no garbage coming into your data stream, okay? So, metadata. Look into the database and check for the symptoms, okay? Otherwise, you might be thrown off. You can speculate that if a case was notified as SARI, is because the individual was in fact presenting as SARI cases. But if the symptoms are not reported into the database, you cannot guarantee it. And then there is an issue of, well, how much assurance I need in the analysis that I want to do. If I want to evaluate, for instance, what are the, the population more at risk for a given infection, restricting myself to case definition is a way to guarantee that I'm not introducing spurious data. Okay? If I want to look only at trends, I might relax that and look to all the cases that were notified and make way and don't take into account the actual symptoms. But for being, it's, again, depending on the analysis that I want, it's better to lose some cases, but be sure that what I have is actually related to what I want, than run the risk of throwing spurious data into my analysis. Now, just to show a little bit what are clear impacts of that, this is analysis that was done recently in terms of the incidence, the weekly incidence per 100,000 individuals in Brazil, looking at that same data for different viruses and different age strata. So in the top left panel is regardless of reported symptoms. So you can see, for instance, that for, and this is for the, sorry, between weeks 10 and 17 this year. You see that for respiratory syncytial virus that affects mostly in terms of hospitalization young children, very young children, we had a weekly incidence of about 15 new cases per 100,000 individuals, while for if we restrict ourselves to cases that respect the case definition, is a little bit lower. Fortunately for us, RSV is one of the least affected by lack of reporting or misreported data, but for the other diseases, we can have a great impact on that. But so this is one way to look into the data, right? So accumulated incidence. Now, if we look at the actual trend, so again, the left-hand side is regardless of reported symptoms. On the right-hand side, applying symptoms filter to guarantee that the case definition is respected. Now you can see now the black line here for each age strata is the total number of SARI cases by week, new SARI cases by week, and each of the color lines are associated with SARI cases positive for different viruses. And you can see, comparing those two panels, that in terms of, even though the volume is different, the trend is more or less the same, right? So what I see here is that if my focus is on the trend, there isn't much of an issue to either take into account symptoms filter or not, okay? But to assess the risk, that is, it is likely to have an impact, okay? Especially if I want to compare different viruses for the same syndromic surveillance, okay? Is that clear so far? Now, finally, if there wasn't enough issues already, there is the big difference between what is going on right now in a given population and what is already in the database for that same population. Why is that? Let's think of the evolution of the information flow associated with any given case. So an individual gets infected somehow. Usually, we have no clear way of identifying when the infection happened, right? So the process of infection itself, usually we have no clue when it happened, okay? So what we use as a reference time frame for case counts is in terms of symptoms onset. So whenever an individual starts to present the symptoms associated with what I'm trying to track, this is what I will use as the event date. So when the case presented itself, okay? This is what is going on. This is the actual situation, right? But then there is the time for that individual to seek medical care, right? Be it for an hospitalized case or for an ambulatory case. Usually there will be a time frame between those two events, symptoms onset and seeking medical attention, right? Again, think of respiratory infections. How many of you seek medical care the first day that you start to have a cough or a runny nose? Never, right? Never. Usually individuals wait for a week, 3 days, whatever, to then seek medical attention, right? And it also might depend on the severity. If I maintain the symptoms for several days, but they are still light or mild, I might neglect seeking medical care. This individual will be completely lost in my notification process, right? If he doesn't seek medical care anytime at all, it's completely lost. But even for those that do seek medical care, there will be the time difference between onset and medical attention. This is already one delay. Now, from the day that the individual seeks medical attention and is identified then as a suspect case for whatever, there is a process of reporting that case, right? And usually, this might involve two steps. One is filling out the local form, be it digital, be it on paper, okay? But this is a local form. And then there is the second step, and this we call notification date. The notification date is the date when the case is notified somewhere, usually the notification sheet, okay? But then there is a process of getting that sheet out and inserting into the official centralized database. Okay, in Brazil, especially for national surveillance system, the date in which the data is uploaded to the national database. In terms of surveillance for individuals that are analyzing the data stream, when a case is visible, accessible, only after the digitization date, right? Only after the data is inserted into the database. Not when it actually happened. What is the impact of that? So here is an example from illustrating just an arbovirus case. So the mosquito here represents the infection itself. The thermometer here, the date of first symptoms, then visit to doctor, and then insertion into the database. Now, if we are at this moment in time, so in terms of infection, we had already 1, 2, 3, 4, 5, 6 cases that already occurred, right? From those, only 4 had been observed at a healthcare facility. Okay, those 2 did not seek medical care yet, and they might never seek medical care, in fact, but take into account only those that do, that are notified at any given point. So we have 4 that the network already identified, but from those, only 2 had already been inserted into the database. So out of the 6 cases that are active right now, or that had occurred within this time frame, I only see 2 in my database. And of course, these have an immediate impact in my ability to assess what is the current situation, right? Because I'm only seeing a fraction of cases, right? And just to give you an idea, this is, again, for study cases alone, from the same time frame all the way from 2014 to 2 weeks ago. And you can see that, and so here in the x-axis, you have the number of epidemiological weeks between the symptoms onset and the digitalization date, so the date that the case was entered into the database. Okay, so when it's actually visible in the system, and you can see that historically only 10% of the cases are inserted within the same epidemiological week, and we have to wait about 4 weeks, so more or less 1 month, to have 80% of the cases that are already happened. This has a huge impact on my capacity to evaluate the current situation. Okay? And I'm not showing you here, but the pattern here also changes a lot with the territory. For example, there are municipalities that centralize the uploading effort in the on the municipal health secretariat. So all the hospitals fill out the sheets, they send those paper sheets to the health secretariat, and at the health secretariat, they upload to the database. Of course, in this type of setting, each healthcare facility will not be sending out sheets every single day. They will accumulate notification sheets to send on a specific day of the week. And it might vary. It might vary with the volume of cases, for instance. It might vary. It might depend on the number of the size of the staff dedicated to filling out those forms. And the same thing happened in terms of the health secretariat. The ability to, once receiving this huge basket of notification sheets, upload that information to the database, again, depends on how many dedicated individuals I have in my healthcare, in my public health secretariat to perform that particular test. If I have more individuals, it will be likely to take a lower time. If I have lower individuals, it might take longer. Yes? And there's also another important thing there, because usually what is written out in the guidelines, so specifically for the mandatory notification of diseases that are 24-hour notification, the notification date that is associated with that process is a notification sheet, not a database entry. So even for diseases that must be notified within 24 hours, the 24 hours is in terms of filling out the sheet, not database entry. Yeah. And there is also another issue there. So this is already a big of a problem. And also, we have to take into account that we are assuming here just the fact that the case is being notified into the database. Now, if I want to analyze the lab results, then there is another time window there. That is the time to run the test, and not only run the test, but update the database with the test result, which is, again, is another process. It's one thing to have the result in the lab, and another thing for that information to go up into the database. The same thing, the same thing is true for the evolution of each of those cases. We have the time, the typical time between, for instance, thinking about hospitalized cases, the typical time window between being hospitalized and become cured or deceased, right? And those can vary, right? They might not be the same. So the time to heal and the time to unfortunately die, they might be different. But again, it is one thing to know that the individual either became cured or died, and it's another thing to have that information uploaded into the database. Okay? So here is just taking into thinking about the evolution itself. So what is actually going on. So we have here for influenza A, syncytial virus, and SARS-CoV-2 SARI cases, the distribution of time from symptoms onset to case evolution. Remember, just SARI cases, so individuals that were either hospitalized or died. And you can see that we have more or less the same time frame for influenza and syncytial virus. For COVID, it takes a little bit longer either to be cured or to become deceased. And between being cured or dying out of the disease, the median time frame is more or less the same, but the dispersion is a little bit different. Okay, so the extreme values are usually a little bit higher for those that become that ended up dying at some point. Okay, but then again, so what we know from here is that if I look at my database right now, I cannot use all of the cases that are there to evaluate the lethality associated to that disease. Because some of the cases that have been already notified, they didn't have enough time to become cured or deceased. Okay? So I have to restrict myself, my analysis, to at a given time point where this effect is already minimalized, or to use statistic methods that take into account this process to actually be able to evaluate the lethality. Okay? By lethality, I mean the probability of dying given that the individual was presented as a SARI case. Okay? So with this, I finish what I had prepared for today. So this was just a big, well, not that big, but there's still a lot of issues, but at least a quick overview of some of the details that I must familiarize myself before putting my hands into a data of notification case and plugging in to my propagation or dissemination model, okay? Because if I don't, all of those things that we discuss here will have a huge impact of what comes out of my analysis. Because what I will be looking at might be completely unrelated to what is actually going on right now. Okay? This is paramount, okay? To avoid making important mistakes in our analysis. Now, in the next few days, we will go over some methods of trying to compensate this process in particular. Okay, so how, given that we know that there is a delay between symptoms onset and database entry, how can we take that into account to estimate what is the current situation for a given disease? This is one of the things that we will be discussing, and also another thing that we will try to go over is the process of estimating activity threshold, so epidemic threshold, and seasonal pattern for endemic diseases that have a seasonal pattern. Okay, is it good? So thank you for your attention, and this is it for today.